Hello, teenagers. This is Mr. Williams, and I am making you a video. I'm making it on Saturday, which is, I think, February 1st. So you should be watching this on February 3rd in the classroom with your sub. Now, I don't expect this to take a ton of time. I just want to talk to you a little bit about momentum and impulse. And as a result of this conversation, you should be able to work on the handouts that I gave you on Friday. All right, let's do some math first. You all know Newton's second law, F equals ma. Acceleration is equal to the change in the velocity divided by time. So you can, if you look over there on the left, I guess from your perspective, the right-hand side of the classroom, where the equations are, under translational motion, you'll see Vf minus Vi is equal to At. If you divide both sides by t, then you'll get this definition for the acceleration. The acceleration is the change in velocity over time. And we've talked about this many times before. I'm now going to replace acceleration here with this definition. So that F is equal to m times the change in velocity divided by time. All right. If I multiply both sides by time, then time cancels out on this side, and I get force multiplied by time is equal to mass times the change in velocity. Hold on, I gotta close my classroom door. Some random strange children are creeping around in the hallway. I don't know why they're here on a Saturday, but whatever. Okay, so this says force times time is equal to mass times the change in velocity. We know from earlier that that momentum is mass times velocity is momentum. So the change in momentum is going to be equal to the change in mass times velocity, which is the same thing as this. So we're going to replace the change in momentum here. So force times time is equal to the change in our momentum. In words, force multiplied by time is the change in our momentum. We have a word for this, force times time. Force multiplied force multiplied by time is called impulse. And the symbol is capital I. This can be a little confusing later if you're in AP Physics because we use capital I for something else. But for now, you don't need to worry about that because all we're going to use I for in regular physics is for impulse. So then the equation becomes impulse is equal to the change in momentum. And impulse is also equal to force times time. So I hope this makes a little sense. We started with Newton's second law. We went to the definition of acceleration. We plugged it in and rearranged it. We got that force times time is equal to mass times the change in velocity. Mass times change in velocity is the change in momentum. We plug that back in. So we got force times time is the change in momentum. And I told you just a piece of information for you. The force multiplied by the time is called impulse, and its symbol is I. So impulse is equal to the change in momentum, and the impulse is also equal to force times time. Let's talk a little bit about what impulse means. Well, if you run into, let's say you're driving your car, if you run into a brick wall, your car is going to come to a stop really, really fast. And the people who are in the car are going to feel like they experienced a huge amount of force. Their bones will be broken. They may die. They're going to get really hurt. And that's terrible. If instead of running into a brick wall, you're going the same speed in your car and you ran into a couple bales of hay that were not tightly bound with wire, they were just fluffy hay. So maybe not bales of hay, maybe just a haystack. So if you ran into an enormous haystack with your car going the same speed, it's pretty likely that you would not get hurt, at least not badly. You might get a little bruise or scrape or something, but you're probably going to be fine. And your car might even be okay. That's really strange if you think about it at first, at the old way, because if a car comes to a stop and it was going the same speed initially, then the change in the car's momentum is going to be the same. It might seem like the change in the car's momentum is going to be the same when you hit the brick wall compared to when you hit the haystack. But what's different? There's a difference, and that difference is in how long it takes you to come to a stop. So it's the time part here that makes a big difference. It takes you very little time for you and your car to come to a stop when you run into a brick wall, but it takes a much longer amount of time for you to come to a stop when you and your car run into a great big pile of loosely dropped hay. And so if the time goes up, then the force has to go down to balance this side. See, the change in your momentum is going to be the same whether you hit the brick wall or the haystack, because in both cases the car had the same mass, and in both cases the car had the same velocity initially, and in both cases the car had the same final velocity because it came to a stop. So let me just restate this. So you're going down a road, you're going 50 miles an hour, you run into a brick wall. So your initial velocity is 50 miles an hour, your car's mass is the mass of the car plus you inside of it, and then you come to a stop and your final velocity is 0. So the change in your momentum is going to be a number. I'm not going to calculate it. And then you run into a haystack. Let's consider that again. So you're going 50 miles an hour. The mass is you plus your car. So you can calculate your initial momentum. And then you hit the haystack and you slow down to a stop. So your final velocity is 0. So your initial velocity is the same, the initial momentum and velocity is the same, whether you hit the haystack or the brick wall. And your final momentum is the same, whether you hit the haystack or the brick wall. So the change in your momentum is the same in both cases. But there's something is different. And that something is the trade-off between force and time. So because then the number here for hitting the brick wall, the force is going to be really big and the time is going to be really low because you multiply a big number by a small number. They counteract each other, kind of. If you run into a haystack, well, the time will be much larger. So what's going to happen to your force to balance it? The force is going to have to go down. So as the length of time over which the collision occurs goes up, then the amount of force that you experience at any one little instant of time is going to go down. But if the time goes down, the force goes up. It's because they equal the same amount of change in momentum in both cases. Sorry, I'm a little under the weather today. I feel like some of you probably understood what I just said, and some of you are probably a little confused. So I'm going to make up an example. I'll just put some numbers together for what we just said. Suppose you drive, let's make it a bicycle, not a car, your bike, which is, I don't know, 40 kilograms. So let's say that you're, I don't know, 70 kilograms. Suppose you, 70 kilograms, drive your bike 40 kilograms into a brick wall. Coming to a complete stop afterwards. Over. Let's see, how long do you think it takes to come to a complete stop when you crash? Not a full second, maybe, I don't know, let's say half a second, over 0.5 seconds. So over half of a second, your bike and you come to a complete, terrible, awful stop. That's not nice. Further assume your initial velocity was, I don't know, 10 meters per second forward. Calculate the force you feel. Your body experiences. Next, repeat these calculations if you hit a haystack instead and took 5 seconds too slow to a stop. All right, here's my made up problem. Suppose you, 70 kilograms, drive your bike 40 kilograms into a brick wall. That says way. Oh my goodness. Wall. Coming to a complete stop afterwards over half a second. Further, assume your initial velocity was 10 meters per second forward. Calculate the force your body experiences. Next, repeat these calculations if you hit a haystack instead and took 5 seconds to slow to a stop. All right. So there's the before situation. Here's your bike. Here's your handlebars. Here's you. Whatever. I hate trying to draw stuff. So, yeah, I know my drawing is terrible. So your initial velocity is, what did it say? 10 meters per second forward. And your initial mass is going to be the mass of your bike plus you. So 70 plus 40 is going to be 110. So So then your after picture. Oh, what's your final velocity after you come to a stop? Well, that's real easy. So, but I got to draw a picture. So here's your bike in a crumpled mess. That's your bike. And here's you. With a sad face. Whatever. Okay, so there you are. And your final velocity is equal to 0 meters per second. And your mass is, the mass of the two things is still 110 kilograms. Actually, we should have like a tier. 2 tiers. Okay. So the change in my momentum is equal to the initial momentum. Well, let's not do it that way. Let's calculate the initial momentum first so that I'm not confusing you. So remember that the sum of all momentums initially equals the sum of all momentums finally. That's conservation momentum. So let's find the sum of all momentums initially. Well, there's only one object, so then we just need to find one momentum. That's P1 initially. And P1 is M1, V1. P1 initially, M1 initially, which is 110 kilograms times 10 meters per second. Which is 1100 kilogram meter per second. So that's my momentum initially. Let's repeat the same calculation for my momentum finally. Sum of all momentums finally. There's only, let's say you're still attached to your bike some kind of way. So that there's only one object, so it's momentum finally. So that's going to be mass 1 finally, velocity 1 final. So that's going to be equal to, I mean, it's silly to even do this, but I know some of you want some help with this. So here we go. Oh, my mic is in my sink. I hope you were able to hear me so far, but if not, I just moved the mic. And I'm not redoing the video. So then 110 kilograms, and the velocity is 0. So that is 0. Now we're going to do a calculation we haven't done before, which is the change in momentum. So this symbol delta, if you didn't know, this is a Greek letter delta, G-R-E-E-K, Greek letter delta, means, quote, change in, or final minus initial. Okay, so anytime you see this, I'm going to put a little box here. Anytime you see this Greek letter, delta, this is a lowercase delta. Delta is a Greek letter that became the letter D in our alphabet that we use every day. But the Greeks had this letter as delta. And nowadays, when mathematicians and scientists use it, what they mean is the change in. And that means you take the final value and you subtract the initial value from it. So the change in momentum is going to be PF minus PI. So that means, what is our final? Our final is 0. So 0 kilogram meters per second minus our initial value is 1100 kilogram meter per second. So the change in our momentum is negative 1100 kilogram meters per second. Now, according to what I showed you earlier, the impulse is equal to the change in momentum and impulse is force times time. So change in momentum is equal to force times time. So the change in momentum is equal to force times time. And my question asked me to calculate the force your body experiences. And it further told me that you came to a complete stop over half a second. So now I know the change in momentum, I know the time, so I need to just find the force, because that's what I need to do. That's what I was asked to do. So if I divide both sides by time, I'm going to get force is equal to the change in momentum divided by time. Change in momentum is negative 1100 kilogram meter per second. And I'm going to divide that by 0.5 seconds. Oh, no wonder that you're hurt. You might even be dead. So that means it's negative 2200. Now it's kilogram meter per second squared, which is in Newton. So, oops, I got an extra zero there. 2200, not 22,000. So that's negative 2200 newtons of force. But what does the negative mean? So let's think about that. The negative means that the force is going in the negative direction. So if you drive towards the brick wall and you're driving in the positive direction, then what's the negative direction? Well, that's the direction opposite your movement. So you're going this way, and that would be the positive direction. The force is in the negative direction. Does that make sense? Of course it makes sense. You're running into the brick wall, the force is going in the negative direction. So that's why the negative makes sense. That's why the delta is final minus initial, so that you get the negative. And it tells you the truth of what really happened. Okay, now we've calculated this is the sad story for when you run into a brick wall. Let's look at the story, which will be a little happier when you run into the haystack. So this is brick wall. I don't need to do any of this. This is all going to be the same for the haystack because you have your initial velocity. It's not going to change. You have your final velocity. You're going to be still stopped after you run into the haystack. You're going to, so all this, the before and after is going to be the same for the haystack as it is for the brick wall. So I'm just going to use those numbers again. What's going to be a little different, even this is the same. The change in your momentum is going to be the same. What's going to be different is this little bit here. So I shouldn't have written brick wall here. I should probably have written it here. Brick wall, because this is still general. This up here is still general for any situation. So now let's just like come down a little bit. I don't even know why I have this square still here, but just to make it look nice, I'll draw a little line, and then instead of brick wall, I'll have haystack. It's the same kind of deal. F is equal to the change in momentum over time, except now my time is different because my haystack, it takes longer to slow down. So it's still negative 1100. Oh, God. Okay, so 1100 kilogram meters. Sorry, guys, I just woke up and I'm feeling like not very good. So 1100 kilogram meter per second, and I'm dividing it by what? How much time? That's on the other side of the sheet. Nope, it's not here. It's up here. 5 seconds. 5 seconds. It's going to take me 5 seconds to come this out. So 1100 divided by 5 seconds. Now I got to go find my calculator. You guys need to look around your house and see if you have my calculator. My good one is gone. So let's see here. 1100. Well, I don't know. Maybe I took it home and maybe it's laying in a stack in my study. I need to look too. Okay, that's 2200. That's a lot. No, that's not 2200. That's 220. That's a lot better. Yeah. 220 newtons, and it's negative because there's a negative in front. So look at these two situations. If you run into the brick wall, your body experiences a force of 2,200 newtons. But if you run into the haystack, your body experiences a force of 220 newtons. Would you rather be hit by this much force or this much force? Well, personally, I'd rather not be hit at all. I don't like to get hit. But if you had to get hit either by a brick wall or a haystack, this is why I'd rather run into a haystack than run into a brick wall. So impulse really matters a lot. So this is why you may have seen, like in old-timey movies or something, like if a building is on fire and people are trapped on the top stories, then back in the old-timey days, like in 1910, 1920, even before that, in the 1800s, the firemen would come and they would see the burning building and people were like all scared and crying and they thought they were going to die. And the firemen would take out a great big blanket and they'd stretch it really, really tight. And they would say, jump. And all the people that were up at the top of the building would jump off and they would hit, instead of hitting the hard ground, they would hit the blanket that the firemen had stretched. And then they could be okay. And they might break their leg or something, but they wouldn't just die and be smashed to bits. Let's think about why that old-fashioned technique of stretching a blanket would help. So let's go back to our equation here, which is somewhere. Let's think about the change in momentum. Well, no matter how big or small you are, the Earth is going to pull on you so that you accelerate at 9.8 meters per second every second as you fall down. That means that your momentum, which is going to depend on your velocity is going to be the same. Jumping off a burning building, your velocity is going to be the same when you hit the ground, no matter whether you're a really heavy person or a really skinny person. So that the change in momentum is going to come from your velocity just before you hit the ground compared to your velocity after you slow to a stop. And every human being, if you jump off the same height, you're going to have the exact same velocity just before you hit the ground and the exact same velocity after you've come to a stop. So your change in momentum is going to be the same whether you're a heavy person or a light person if you jump from the same height. So everybody jumping from the burning building is going to have the same change in momentum. The question is, can we save you? And that comes down to this interplay between force and time. If you just smash into the concrete jumping off of a 10-story building, then you're going to slow to a stop very, very quickly. You're going to come to a stop so quickly, much less than a second, much less than half a second. You're going to come to a stop so quick that the force is going to be really huge. It'll do terrible things to your body, and that's not what anybody wants. So instead, if you can increase this time by just a little bit, this force will come down dramatically. So when the firemen stretch that blanket, you hit the blanket, and even if it tears the blanket from the fireman's hands or it rips a little bit out of the fireman's hands, the fact that you're slowing down, you have more time to slow down while you're striking the blanket, that decreases the force a lot. So you may actually still fall and hit the ground underneath the blanket and get hurt a lot. You may break your leg or your back or something, but you would still be alive because the force is so much less. Of course, nowadays we have even better things for firemen than just a blanket. We have these, like the bouncy castle that you might have played in for a birthday or something. So they take a piece of plastic and they fill it up. And when they have to jump off a building or something, they'll land on the bouncy castle toy thing. Except it's not a toy; it's an actual tool that firemen use nowadays, and that gives you a lot more time to slow down. And you may not even hit the ground underneath if they've blown it all the way up and it's really thick and big plastic. So you fall down and you smack into the plastic. And you may take like 2 seconds to slow to a stop if it's really huge, or a second and a half. instead of like 100th of a second. And so the force is so much smaller. That's great. That's actually why trampolines work. That's why trampolines are so much more fun to jump on than jumping on the concrete. Okay, I've kind of taken my time here. I hope this is helpful to you. You should be able to use this to do the work that is in your handout that I gave you on Friday. If you have any questions from the handout on Friday or questions from the handout the day before, you can go up to the front left of the classroom in 5th and 6th period today. I have written on the front of the board in purple some boxes, and you can request specific problems that you want me to do tonight, because I'm working at the district office today, but I will be coming back to my classroom tonight after school and making a video for you for tomorrow. And you can request a particular problem that you need help on, that you're confused on, and I'll make a video for you tonight. All right, well, it'll be tonight for you. All right, kids, have a good day and good luck thinking about impulse and momentum, force and time. And be nice to Mr. Knight.